In part 1 of our lesson on the unit circle and circular functions, you're going to derive the definitions of the circular functions. So let's start off considering a circle whose radius is equal to 1 unit, and that's where the term unit circle comes from. Now, S is going to stand for the arc length, which is a physical distance from the point 1, 0 over here to the point xy. So the units of S would be feet or inches, miles, kilometers, meters, etc. S is a physical distance, the distance you would walk if you started here at the point 1, 0 and walked along the arc length until you got to the point x, y. Now S is what we call a directed distance, in that if S is positive, that means you're walking counterclockwise. If S is negative, then that would mean you're walking clockwise around the circle. Theta is, as it's been all semester long, theta is the angle in standard position. So there's a big difference between S and theta. So someone turning through an angle of theta stays right here at the origin. They just start out looking at the point 1, 0, but they don't actually walk anywhere. They turn in place until they're looking towards the point x, y. Whereas someone who is traveling on S actually moves a physical distance from 1, 0 over to xy. Now remember from an earlier lesson that the formula for arc length is that S is equal to r times theta, and of course theta is in radians, Now, if we are on the unit circle, which is what we have pictured over here, the unit circle, meaning the radius is 1 unit, on the unit circle, we know that r is equal to 1. So this equation becomes S is equal to 1 times theta. And of course, 1 times theta is just theta, so we get that S is equal to theta. And this is only on the unit circle. Now, S and theta still will have different units because remember, S is a physical distance, so it will have units of feet, miles, inches, centimeters, where theta we know is in radians, but numerically they will be equal to each other. So if theta is 1 radian, S would be 1 foot or 1 inch or 1 mile. Okay, so they're not equal to each other in units, but they're equal to each other in magnitude. Now, if we start from the trig definitions, and then we'll substitute in the fact that r is equal to 1 on the unit circle. So we know that sine of theta is equal to y over r, but we know that on the unit circle, r is equal to 1 and S is equal to theta. Then that means that this definition would become the sine of S is equal to y divided by 1, which means the sine of S is equal to y. So we'll come down here and fill in our definition. The sine of s is equal to y. Next, we'll look at cosine of theta, and its trig definition is x over r. Now again, on the unit circle, we can make those substitutions and we get cosine of s, because we're substituting s for theta, is equal to x divided by 1, which is equal to x. So we can come down here and say cosine of s is equal to x. Tangent of theta, using the trig definitions, is y over x. Now on the unit circle, the only substitution we can make is that theta becomes s, so this becomes the tangent of s is equal to y over x. And we can take that, put it down here in our definitions. And then we can use the reciprocal functions. If sine of s is equal to y, then cosecant of s is going to be 1 over y. If cosine of s is equal to x, then secant of s will be 1 over x. And if tangent of s is y over x, then cotangent of s is going to be x over y. Now these are called the circular functions. Notice it's a different name. They're not called the trig functions. So the circular functions only exist on the unit circle. That's the only place that the circular functions exist. Now recall that the equation of a circle whose center is at the origin and whose radius is equal to 1 is given by the equation x squared plus y squared equals 1. You learned that in your college algebra class. Now, if we substitute in the circular functions that we just learned, instead of x, we're going to put in cosine of s. So we have the cosine of s squared plus, we're going to substitute for y and put instead sine of s. We get sine of s squared, and that has to equal 1. And you notice that that turns into the very familiar Pythagorean identity. So we have cosine squared of s plus sine squared of s is equal to 1. So the Pythagorean identities will work for the circular functions. Next, we'll try an example where we have to evaluate the 6 circular function values of s. Now we're given this diagram here, and we know we're on a unit circle because since the center is here at the origin and we see that a point on the circle is 1, 0, we know this distance is 1, so we know that this is a unit circle. Once we're on the unit circle, that means the circular function values will apply. So now using the definition, we know that the sine of s is defined to be y. Now remember that s is this physical distance that the particle travels from this point here at 1, 0 down here to this point at 3/5, comma, -4/5. S is not an angle anymore. S is this physical distance. And the circular functions say that the sine of S is going to equal the y value there. So there's actually nothing to calculate here. We just write down -4/5. The cosine of S is defined to be x. Once again, we look at the picture and see that our x value is 3/5, so that's the cosine of S. The tangent of S is defined to be y over x. So using our diagram here, we've got -4/5 divided by 3/5, which of course turns into -4/5 times 5/3, which once those 5's cancel out, we know is going to equal -4/3. The cosecant of S is defined to be 1 over y. Now we know that just means the reciprocal of y, right? It's going to be 1 over -4/5, which is equal to -5/4. The secant of S is equal to 1 over x, which is going to be 1 over 3/5, which is equal to 5/3. And finally, the cotangent of S is going to equal x over y, which is 3/5 divided by -4/5. And hopefully now you're getting more comfortable with, rather than having to write this as we did up here by multiplying by the reciprocal, hopefully you can start to see that when I have a 5 in a denominator here and a 5 in a denominator here, you can cancel those out, and we're left with -3/4. In this example, we have to find the exact circular function value of each. The first problem is asking us to find the sine of 3 pi over 4. Now in this context, this of course is S is equal to 3 pi over 4, but we know that S is numerically equivalent to theta. So you can really proceed with this just like we've done all semester long with the 4 steps that we've been using. So step 1 is to draw a picture of theta, and 3 pi over 4 we know is in quadrant 2. Here's theta, 3 pi over 4. Step 2, we have to find the reference angle, and we know that the nearest x-axis here is at pi, which we can think of as 4 pi over 4. So we know that our reference angle is going to be pi over 4. All we have to do is subtract 4 pi over 4 minus 3 pi over 4 to get 1 pi over 4. Step 3 says to find the trig function value for the reference angle, and we know that our trig function is sine, so we're going to find the sine of pi over 4 on our reference angle chart, and we see that that is radical 2 over 2. Step 4 says to get the positive and negative sign based on the quadrant, And we know that in quadrant 2, sine theta is positive. So then that means that the sine of 3 pi over 4 is going to be positive radical 2 over 2. So let's pause the video, try the next 3 examples on your own, and then restart the video to check those answers. This next problem asks us to evaluate the cosine of 7 pi over 6. We know that 7 pi over 6 lives in quadrant 3. The nearest x-axis is pi, which we think of as 6 pi over 6. So theta r is going to be 7 pi over 6 minus 6 pi over 6, which is pi over 6. Our trig function is cosine, so we go to the special angle chart. We see that the cosine of pi over 6 is equal to radical 3 over 2. Next, we have to get the positive and negative sign. And in quadrant 3, we know that cosine theta is going to be negative. So that means that the cosine of 7 pi over 6 is going to be negative radical 3 over 2. Next up, we have the tangent of negative 5 pi over 3. Now, negative 5 pi over 3 lives in quadrant 1. We know that the nearest x-axis would be here at negative 2 pi, which is negative 6 pi over 3. So our reference angle is going to go from negative 5 pi over 3 to negative 6 pi over 3, which of course is 1 pi over 3. So our reference angle, pi over 3. Our trig function is tangent, so we're going to need the tangent of pi over 3. We go on the special angle chart, and the tangent of pi over 3 is radical 3. We know that in quadrant 1, tangent of theta is going to be positive, so that means the tangent of negative 5 pi over 3 is equal to positive radical 3. Next up is secant of 7 pi over 4. First we draw theta. We know that 7 pi over 4 is in quadrant 4. The nearest x-axis is 2 pi, which we know is 8 pi over 4. So then that means our reference angle is going from 7 pi over 4 to 8 pi over 4, subtracting, of course, and we get 1 pi over 4. Our trig function is secant. So we're doing the secant of pi over 4, which means we have to do 1 over the cosine of pi over 4. Off the special angle chart, we know the cosine of pi over 4 is radical 2 over 2. So this becomes 2 divided by radical 2. And when we rationalize, it becomes 2 radical 2 over 2, and those 2's will cancel. So we see that the secant of pi over 4 is going to equal radical 2. We are in quadrant 4, and in quadrant 4 we know that secant theta is positive. So then the secant of 7 pi over 4 is going to be positive radical 2.